Oh. Okay, so we're ready to roll. It's 101. Exams, the mini exam ones, they're here if you need to pick them up. A little bit about the mini exams. I was going to send an email to talk about them, but I decided I would talk in class about it. So first thing, make sure they're stapled. I didn't take off maybe 1 point if you didn't staple it. Everything was based out of 60 points because there were 6 problems. I graded each one on a 10-point scale. So the max you could have got was 60 out of 60. So if you add up the points and they're not making sense, that's how I'm doing it, right? So if you missed 10 points, you got 50 out of 60. Staple, neatness was pretty good. I could read mostly everything. What else? There was some confusion about the computers, right? So like, make sure you read the instructions carefully because I said you can't use a computer to solve equations on that test. You could use it for anything else, like looking up what a regular pentagon is, for any other thing you could have done, but just not for solving an equation like number 3, right? Number 3 on the test. What I was really hoping for there was for you to use synthetic division, for you to use that test where you look at the leading coefficient and the number in the back and you create all these possible rational zeros and then use synthetic division. That's the cleanest way to do that problem. There were some other people that did it by brute force and weird sort of other things, which is fine, but it would be easy for me to give you a problem where that brute force would become like not tolerable. And so we need a method. And the method I was hoping for was for the synthetic. So again, in the future, if you're working on a test on these mini exams and you feel like you're going down this rabbit hole that seems like we're too far off track from what this class is about, like get in touch with me. That's the whole reason I tell you, reach out, ask questions, right? Because I don't want you to go spend 3 days on something that I think you could knock out in an hour if you just kind of knew which way to go, all right? So I really do want to have a little more dialogue back and forth between myself and you with these mini exams, because I want to kind of see the way you think, the way you're approaching things. So don't hesitate to reach out. It's worth it for you to get a good score, right, on the test, rather than assume that you're doing it right and then I start taking points off. So any questions on that? I'm not going to answer specific questions on specific tests right now. There was something else. Reading instructions, staple, name. Oh, if you have group, right? If you have a group, put your name and then your group members separately. Don't mix them up because I don't know who's who, right? Yes?
Do you prefer a call or a text if we're stuck on something?
A call or a text? Well, the text obviously didn't work the other day for you, but if I don't respond to a text, call me. Okay. But normally a text is a good way to start. And I always ask that when you text me, if you're working on like number 3, like send me a picture of the problem because I don't remember exactly what number 3 on mini exam 2 is, right? Like send me a picture of the problem. If you've done any work, send me a picture and then just kind of like summarize like what your question is. And I'll get back to you pretty promptly, right? I mean, Hunter, I'm pretty available. I mean, even yesterday in Super Bowl Sunday, I was practically on my phone the whole night helping students out. So please reach out. So does that answer your question? Okay. All right. Okay, let me see. Yes, this is yours. And here we go. Okay, so this is the first test, right? Remember, we're going to get 8 to 9 of these. And you get to, I'm only grading your best 6, right? So if this didn't go well, there's always another one. The next one's due on Wednesday. And I've only had one student ask for help. So, and you're supposed to be working alone on that one. So don't wait till Wednesday morning. My enthusiasm to help you is inversely proportional to the amount of time left, right? Well, no, take that back. If the time left gets small, my enthusiasm gets small. So it's directly proportional, right? The closer we are to the deadline, the less willing I feel to help you because you've waited till the end when I've told you over and over, don't wait till the end. If you ask me in the beginning, I'm like, let's do it. Let's get into this, right? All right. Okay, we are going to move. We are going to crank through today. So I need everyone to let me plow through this stuff. If you have questions, I want you to ask, but let me develop the ideas first before we get, too much off track. Anything else before we begin? Okay. I'm going to pass the sign-in sheet around because why not? All right. We are in Chapter 10, Section 8. We just finished talking about, vector functions, these things called space curves, right, which is just curves in three-dimensional space. And now we're going to talk about arc length and curvature. This is not going to take us the whole class. We will finish this up hopefully in the first third of the class. There's not a whole lot here. All this section says is we can talk about two different things when it comes to curves in three-dimensional space now. Also in two-dimensional space, I should just say, in either R2 or R3. First topic is arc length, and this is something that we talked about in Cal 2, right? If we had a function, we could figure out the arc length, which would be the same as like taking that curve off the sheet of paper, stretching it out, and measuring how long it is. We can do the same exact thing in two or three-dimensional space when we're talking about vector functions. So this is just the notes for it. It just talks about what we're going to do. One important thing about this definition, this definition and formula is that if we're going to try and find the arc length of a curve, we have to be talking about a curve that starts at a point, does something, it can even cross through itself like this, and stops. All right? And then we can talk about arc length. It can only traverse that curve one time. Where does it say that? Traverses it one time. So remember we had a vector function that drew a circle? And that if we didn't restrict the domain, it would just keep drawing the circle over and over and over. We are not allowed in this case to actually go over ourselves repeatedly. This formula will break down. So we have to recognize that when we're thinking about the vector function, making sure that it's never going over the same path twice or more than one time. So as long as we're traversing the path exactly one time, then the formula to find the arc length of that curve is going to be, and it's really a straightforward formula, it is an integral, as you might suspect. It's the integral from a to b. Now, a and b are going to be our restrictions on the t. Remember, all vector functions that we've been studying are vector functions that look like this, r of t. T here, right, is our domain, and we're assuming here that t is going to start at a and end at b. So t is some element of this closed interval a, b. That's like time, right? Time, t has kind of been like time in the background. So our integral will be from the start of time to the end of time, if we want to look at it that way. And then what we're integrating is the derivative of the vector function. Remember, the derivative of the vector function is a vector that is tangent to the curve, right? So we look at this curve. If we were to take one specific point on the curve, that vector right there would be r prime of t, right? And at every point, there's a different vector. It changes as we move through the curve. And what we're doing is we're taking the length of that curve, right? We're taking the length of that curve, how long it is. We're multiplying it by this infinitesimal, this what we call the differential, the dt. And what that does is it scales that vector down. It gets the length of this and it scales it down so that what we're doing is we're taking a like infinitesimal measurement of how long that little piece of curve is. And the limit, the integral involves a limit, so we're letting time, basically the increment of time, go to 0. And then the integral, all it does is adds them up. I'm not going to get into the details of that because that's more of a Cal 2 topic. But the integral adds up a bunch of things, right? And what we're adding up is just that tangent vector that's been scaled down. And just add them all up and it'll give us the arc length. So that's it. That's the formula. So all we have to do to find arc length is be able to take a derivative of the vector function, take its magnitude, and then hopefully be able to integrate that, right? So let's do an example. And I think the best example to start with is the unit circle, right? That is the vector function for the unit circle. This is a two-dimensional vector function, right? Cosine t, sine t. And what I'd like to do is find the arc length of this curve from t equals 0 to 2 pi. So that just draws a circle one time, right? And if it's the unit circle, we should expect that arc length to be equivalent to the circumference. And we know that the circumference of a circle of radius r, right? Circumference is 2 pi r, right? That's in general, circumference of any circle. So if this is the unit circle, we should expect that our answer is 2 pi, right? Let's verify that by actually cranking out the formula. So first things first, I'm going to take my vector function r of t. I'm going to take its derivative. And derivatives of vector functions are pretty straightforward. We just take the derivative of each component function, right? Each component function, we take its derivative. So we need that. Now we need its magnitude. So I'm going to take the magnitude of this. And to take the magnitude of a vector function, we just take the square root of the sum of each of those components squared. So I'm going to take negative sine t, square it, plus the cosine t, square it. And fortunately for us, right, this just becomes sine squared t plus cosine squared t. And that's the Pythagorean identity. So this is just square root of 1, which is 1. Right? That's the magnitude of the derivative. We need to integrate that function from 0 to 2 pi with respect to the variable t. So now's the actual arc length. That was just set up. It was just me getting the pieces. Now we go to the formula. The length of the arc is going to be the integral from 0 to 2 pi of this, which is just the constant 1 function, dt. And that's about as clean of an antiderivative as you're ever going to get, right? The antiderivative of 1 with respect to t is t itself. And then we evaluate that from 0 to 2 pi. We plug in 2 pi first, right? 2 pi into t. Then we subtract from that. Then we plug in 0 into t. We get 0, and our answer is exactly what we expected it to be, right? Okay? Questions on that? Yes?
So is the magnitude 1 the distance from the center to the edge of the circle?
No, it's not. Well, it is that, but not. This is the magnitude of the tangent vector, right? So what we're saying is that the magnitude of the tangent vector is always 1. Now, if you wanted to know what the magnitude of the vector function was, you would take the magnitude of this, and do you see you'd still get 1? That would tell you that all your points are always a unit length from the origin, which is a circle. But that's different than what this is saying. This is telling us that our tangent vectors, as we move around that circle, well, I don't have the tangent vectors here. This is just showing we're measuring that length around here. If you were to draw the tangent vectors, they would all be like this, and they would all have unit length. Okay? Okay, let's do another example. Everything I've said here translates into three-dimensional space. So if you have a vector function where you have 3 components instead of 2, right? You have a vector function that has 3 components instead of 2, so now your three-dimensional curve, everything is the same. The formula is exactly the same formula. The only difference is in the computation of that magnitude of the derivative, right? Because you have 3 pieces instead of 2. So we're just going to do this on this example right here. That is an example, I think I showed you all this. This draws a circle in the xy plane. I actually am going to need this today. And what is it doing in the z direction? It's constantly going up. So when we draw this, it's going to look like what? Like a what? Like a spiral? Yeah. I go with spiral. I'm thinking more like a spring. When I think spiral, I think it kind of opens up. That's just my way of thinking. But spring, right? Because it's a constant radius. So it's like trying to draw the unit circle in the xy plane. How do I know it's drawing a circle in the xy plane? Cosine and sine are in the x and y components, right? So it's drawing a circle in the xy plane, but at the same time in the z component, it's growing linearly. So you've got this like that, right? So what I'd like to know is what is the length of the arc connecting these 2 points together, right? So I'm giving you actually 2 points on the spring, and I'm saying what is, if you were to connect those and like go along the curve, what's the length of that? And so the difference between this problem and the previous one, there's two differences. First, this is a vector function in three-dimensional space. That's the first difference. Second difference is I'm not giving you the restrictions on t. Not directly, right? I'm giving you 2 points. And so what we still need to resolve right now is what is the interval, right? What is the interval that we start and stop at? And the way that I think, I pointed this out last class, for this function, it's easy to see what the restrictions on t are because the last component is t itself. So this point right here, 1, 0, 0, that right there is my starting t, right? T would be 0. And then here's pi. So I should be going here from 0 to pi. Does that make sense? It would be a little harder, and it might be harder on maybe a take-home mini exam. You might have to analyze that a little bit more to figure out what the restrictions on t would be, right? But in this case, it's simple. All right, so I know that, right? I need to know the derivative. So let's take derivative of this. I feel like I'm talking faster. Y'all all right? I feel like this is a pretty straightforward concept, so I don't want to get too bogged down on it. There's our derivative. Magnitude. After I do this, I'm going to integrate it. So the magnitude is going to be the square root of, very similar to the previous problem, except we have that third piece, right? These first two, that's going to be the Pythagorean, right? Identity. So that's going to give me a 1, and then I'm going to have plus 1, so this should just be root 2. Another constant, right? We got lucky again. And so now I'm ready for the actual computation. The length of this curve will be the integral from 0 to pi, 0 to pi, and then the square root of 2 dt. And then I just play the same game we just played. The antiderivative of this is root 2t, evaluating from 0 to pi. We plug in pi, we get root 2 times pi. And then minus, if we plug in 0, we get 0. And if I were doing that, I would write it the other way around so that people don't accidentally think that that pi is underneath the root with the 2. I put the pi out front. That's it. That's the length of that curve. I'll show you the picture. I think I have a picture. Yeah, that's it right there. There's the spiral. Okay, you can see looking from the top, it's trying to draw a circle. But if you look at it from the side, it's linear, right? It's a linear growth. And so all we've done right now is we've measured that length right there. I'm only showing, the spring goes in both directions forever, but if we restrict the domain, it's only that portion of the spring, and that's what we are getting the length of. So it's pretty cool. I mean, abstractly, you have any vector function, anything that you can think of that moves in three-dimensional space, if you know the path, like the function, then you can figure out how long that path is, right? Theoretically, if you can do an integral and derivatives. All right, what's next? A harder function, right? Everything we've had so far, right? Our arc length, I'm sorry, not our arc length, our magnitude of our derivative has been a constant, hasn't it? Let's try something a little bit harder, like this one. One more thing about asking for help, right? You can ask for help at any time. It can be, 8 o'clock at night. It doesn't, if you can't make my office hours, don't hesitate. Like, oh, it wasn't 8 to 5. Just reach out. If I don't respond or I say, hey, I'm busy, I'll let you know. All right. I'm just really concerned that nobody's asked for help on this other mini exam that's due in 2 days. I'm really concerned. I'm thinking a lot of you are going to dump this one. Remember, if you don't do the mini exam, that doesn't mean you're not going to see those problems again. We still have a midterm, don't we? So you still need to understand the concepts, because the midterm is going to be comprised of all these concepts, right? Yes?
So you say we have a midterm, does that mean our final is just the sections that we cover after?
That's right. Midterm is first half of the class, final second half. Yep. So anything after we get done with the midterm, none of that, you'll never see that again. Unless it's somehow inherently built into the other part. Yeah. All right. All right, same thing. Good news, I gave us the restrictions on t, right? I didn't give us 2 different points, so we should just crank out the derivative, its magnitude, try the integral, see what happens. So derivative. All right, so the first component function, I need power rule on that, right? So I bring the 3/2 out front, the 2's cancel, I just get 3t, subtract 1 from that power, I get a half. And then the derivative of cosine of 2t is -2 sine 2t. I have chain rule there, right? So I have to take derivative of cosine, which gives me negative sine, and then I take derivative of what's inside, which gives me a 2. So I got a little bit of chain rule to work with there. And then the third component, I get 2 and then cosine 2t. All right, that's my derivative. Any questions on the derivative? Magnitude. All right, so the magnitude of this, I'm going to take the square root, and I've got to take the sum of all of the components squared. So if I square this, I square the 3, get 9, and this is the same as the square root of t. So I square root of t, I just get t. And then let me take my time here. When I square this, I get a 4 from the -2 times -2. When I square the sine, I get sine squared 2t. And then plus here again, I get a 4, and then now a cosine squared 2t. My next line, what I'm going to do here is factor out a 4 on the second 2 terms here. Right, I can pull a 4 out of both of those. And if I pull a 4 out of both of these, then what remains in here is the Pythagorean identity, right? Sine squared of something plus sine squared of that same thing, that should just turn into a 1. So it's not a constant, right? It's not a constant, but I would argue that's not very complicated, right, in terms of a function. And so that's the thing I'm going to need to integrate now. Let me do my integral right here. I'm going from 0 to 1. Square root of 9t plus 4 dt. Okay, so there's different ways people could do this. I don't need any special thing here, right? No integration by parts. I don't need trigonometric substitution. This is just probably a basic u substitution if you're going to do anything, a basic u sub. Let me see, 3/2. I think it's going to be 3/18, 9t plus 4 to the 3/2. I believe that's our antiderivative. I'm just going to check it real quick. Hold on, 2/3, sorry, 2/27, my bad. All right, so if I do this times this, I'm just checking my answer. This times this, what happens? The 2's cancel, you get 3/27, which is 1/9. So I have 1/9, I'm taking derivative, just check real quick. 1/9, and then it's all of this. Subtract 1 from that power, and you get a half. And then derivative of the inside of that is 9, and it kills that off, and you get back that. So I'm not showing that work. Can I leave you all with that, or no? Yeah. Yes? Okay, that's the antiderivative. So ... you could do this, I hope, right? And then now we're evaluating from 0 to 1. And just plug in 1. It's going to not be pretty. Let's plug in 1. We're going to get 2/27. If I plug in 1, get 13 to the 3/2. And then minus, if I plug in 0, I don't get 0, right? I get 2 over 27, and then 4 to the 3 halves. And that would be fine as an answer for me. I mean, that's just some number, right? If you wanted to, you could do this on your calculator, get a decimal, whatever. That would be like an exact. And there's other things you could factor things out and, fine, but we have the number, right? That's the most important thing. Questions on this? Just a U sub from here to here? All right. So here's the curve just for fun. I had the computer draw the curve. That's what the curve looks like. And it's 3-dimensional, right? And so what we did is we found the length of this curve. And so we measured from t being 0 to 1. We measured that right there. Okay, moving on. We now move to the next topic in this section, which has to do with something called curvature, which is a completely different idea than arc length. Arc length was just a measurement of how long some path is. Curvature has to do with measuring how quickly a curve changes direction at a given point. So if you think about, like, you're traveling along a curve, you're at some point, you want to know, the tangent vector tells you the direction you're moving in, but we want to know if we move a little bit more, am I going to be, going like that way, or am I going to turn this way, or am I going to be going like that? Somehow we want to measure how rapid that changes as we move. So we can calculate this thing called curvature at each point. And this is the way we denote it. This is a lowercase k, but it's usually bolded in textbooks. It's kind of a weird k, all right? And there are 2 equivalent definitions for curvature. One of them is this one. Now let me explain what this is. I'm going to see if you remember this from last class. Capital T of t, by definition, is the derivative of the vector function over its own length. We call this the tangent vector. I told you all that when you're traveling along a curve, you have a tangent vector, and that we can always find a vector that's in the same direction but has a length of 1. That's what this is, okay? The first definition of curvature says you need to take the derivative of that vector function, take its magnitude, and then divide it by the magnitude of the first derivative of the vector function. I'm not going to go into why this gives you curvature. That's a discussion for office hours. We sit down, we talk about it. For us, we're just going to say, hey, this measures somehow how rapidly you're changing as you're at a point, if you move to like an infinitesimal point in time. Just, you know what I mean? Like, you're here at some point, change time just a little bit, and then how much are you going to be turning? Like, what's that rate of change? That's one definition. To do this, think about what you have to do this. You have to take the derivative, divide it by its own length. That gives you a new vector. You take that vector, you take its derivative, and you find its length. So you're going to be taking a derivative, finding a length, and then another derivative, finding a length, and then dividing that by the derivative of r. That's the computation for this. The other alternative is to do this one, which just says take the first derivative of r, do the cross product with the second derivative of r, take the magnitude of that vector, and then divide that by the magnitude of the derivative cubed. Now I'm thinking I might offer a bonus. This is not official yet. I might offer a bonus that would replace one problem on any mini exam in the future or in the past. You know how like sometimes you get a problem, you just completely butchered it, right? So I'm thinking about giving a bonus where you show me that these two are equivalent. In other words, you have to algebraically show me that these two are the same. And let me think about it. I want to go through it again because I haven't done that in a while. I want to see what algebra is involved there. But if I forget about it, remind me and I'll come back. All right, so I say here that this formula, this is the one I like. This is the one I prefer to use, this one right here. I do say that this is only good that when we're in R3. And that's because we're doing a cross products. And cross products are only defined in three-dimensional space. So if you have a two-dimensional vector function, you aren't necessarily going to be able to use this. Maybe. There's a workaround. Okay? Let's do an example. Let me write these down over here. So it's the magnitude of the tangent vector's derivative, right, divided by the magnitude of the derivative of the vector function. That's option 1. Or we can do the magnitude of the cross product of the derivative with its second derivative, and then divide that by, so weird, the derivative of the vector function's magnitude cubed. That's just so odd that that's what it is, but it is. All right, so we're going to go back to the unit circle. Right, this draws the unit circle. We just did that. We just found the circumference of that. But now what we're going to do is we're going to use this formula to verify that the curvature of this vector function is constant. Does that make sense to you? Think about if I were to start moving along this circle, right? If you're at any point, right, moving along this circle, do you agree that you're constantly kind of turning at the same rate the whole time? Like your curvature is constant, right? We should be able to verify that with this formula, that we have a constant curvature. All right. So let me get a couple of things in place here. First thing I'm going to do, let's go ahead. I'm going to use this formula. Oh, shoot. I can't use that formula, can I? Can't because it's in two-dimensional space. The workaround. Okay, here's the workaround. What I'm going to do is I'm going to rewrite this vector function, but I'm going to force it into three-dimensional space. So all I've done here is said, instead of looking at this as like living on a flat sheet of paper, imagine it's in three-dimensional space with your z component being 0, and doesn't that still draw the same circle in the xy plane? It does, right? But now we're like stepping into three-dimensional space instead of 2. And if we do that, then we can actually still do cross products. So even though the formula says you can only do this in R3, we can always take a two-dimensional vector function and push it into three-dimensional space. Every time, just replace that with 0, okay? Yes?
That's it. Will you ever specifically require us to use the first one?
I don't care which one you use. The algebra of these, sometimes the algebra of this can be much easier than the algebra of this, but most of the time this one is easier, most of the time. All right, let's do it. So I need the derivative, right? I need the derivative of this. That will give me that part, right? So the derivative of that is going to be negative sine t, cosine t, and 0, right?
Yep.
Hey, when I drew that, I pushed it in three-dimensional space, right? Could I have drawn the circle just shifted up 1? Right, if I moved the whole circle up 1 and drew it, I would get, this would be a 1.